Hello, this video is for STA2023 Statistical Methods, Chapter 7, Section 3, the central limit theorem for sample proportions. Now the central limit theorem for sample proportions says, it gives a good approximation of the sampling distribution without our need to do simulations. If some basic conditions are met, then the sampling distribution of the sampling proportion is close to the normal distribution. So basically what that means is, when the data is proven to be normal or close to normal, then we can make some conditions like z-scores and things like that. We can do some things. But in order to make sure it's close to normal, what can we do? And the central limit theorem says if some basic conditions, condition 1, condition 2, condition 3 are met, then we can say that the sampling proportion is close to the normal distribution. Then we can do more things. So let's look at the conditions. All of them are important and they all must pass. So condition 1, it has to be random and independent. Random and independent. So it's got to be random. And we also have to make sure we have a large sample. The population has to be greater than 10 times your sample size. The population has to be greater than 10 times your sample size. And we'll make sure we have a big population. So n sample size times population proportion has to be greater than equal to 10. And n times 1 minus p has to be greater than equal to 10. All three have to pass. Then we can use this SE formula and we can move on. So the best way to explain this is through a couple problems. So we're going to do some sample problems. The first one's not my favorite, but we're going to do some sample problems. Okay? So here it says, Pet World has a population of 1,000 people, and the proportion of cat people is 25%. We will take a random sample of 100 people. What is the approximate probability that the proportion in our sample will be bigger than 29%? So it's really important to understand the question. So let's see what we have. So in this case, the population is 1,000 people. Again, this is not my favorite problem because the population is only 1,000. Generally, it's all people, or thousands of people, or hundreds of thousands of people, or millions of people. So usually this is not an issue, but since it's 1,000, we're starting with a small population. The number that describes the population is P, which is 25%. And our sample size is 100 people. And our sample proportion, p hat, is 0.29, and we're trying to find out if it's larger than 29%. So let's make sure we understand the question. What we're trying to find out is, knowing that the population is 1,000, and knowing that the population proportion is 25%, 25% of all people are cat people, we're wondering if we ask a random sample of 100 people, what is the probability that our final answer will be 29% or more? What's the chance of that happening, knowing that it's supposed to be 25%? Okay, so that's first. Condition 1, got to meet our conditions. Is it random? Yep, it's stated. Number 2, your population has to be greater than 10 times your sample size. So your population is 1,000 people. Is that greater than 10 times 100, your sample size, which is 1,000? Again, this never happens, or rarely happens, I'll say, that you get the same exact numbers. We're going to go ahead and let it slide, but technically your population has to be greater. And then the third one, n times p, has to be greater than or equal to 10. N is 100, sample size. P, 0.25, gives you 25, it's greater than 10. Check. 100, 1 times, parenthesis, 1 minus 0.25. That gives you 0.75. 0.75 times 100 gives you 75. Is that greater than 10? Check. All three conditions are met. We can assume that the sample proportion is normal, and we can move on. Then we find our SE. Our SE, square root, P, 0.25, parenthesis, 1 minus 0.25, close parenthesis, over 100. Please practice this. This is a common mistake, people typing this in wrong. You should get 0.043. Be careful. Some people also forget that 0. Then, the next part's going to look very familiar. Now we're going to find the probability, which means we're going to find our z-score. So our formula is p hat minus p over our standard deviation. Now this should look familiar from previous sections, but we're going to use p hat, kind of like x bar, minus p, which is kind of like mu, over our standard deviation. In this case, be standard error. So in our case, be very careful. P hat is 0.29 minus 0.25 divided by our standard error, 0.0433. Double, triple check typing that in. You get 0.92. If we're drawing this out, 0.92 would be about here, and we're looking for more than. If we go to our z table and look up 0.92, Table tells you to the left, you'll get 0.8212, but the table always tells you to the left for using the table. But if we're looking for more than, we don't want 82.12%, we want the other side. So 100 minus 82.12 gives us 17.88%. Now that was long, I understand, but the hard part is, what does that number mean? It means the probability that the proportion of people that are CAP people with a sample of 100 people is 29% or more is 17.88%. So again, what does that mean? We know that 25% of people are CAP people. I was wondering, if I took a random sample of 100 people, what's the chance that my final answer is going to be 29% or larger? What's the chance that my final answer will be 29% or larger? The chance of that happening is 17.88%. Now again, understand this number. Why is it kind of low? Because it's supposed to be 25. So we're looking for 29 or more. The chance of that happening is only 17.88%. Okay, let's try another one. According to the Mars Company, packages of milk chocolate M&Ms contain 20% orange candies. Suppose that we examine 100 random candies. What is the approximate probability that the proportion in our sample will be less than 15%? Again, the population is all M&Ms. Think about all the M&Ms in the world. And we're only sampling 100 M&Ms. We know that 20% of all M&Ms, P, 0.20, representing everybody, we're trying to find out P hat, what's the chance of getting less than 15%. So before we get started, we know that it's supposed to be 20%. So the chance of getting less than 15 is probably not going to be very likely, knowing that it's supposed to be 20. It's supposed to be 20. So was it random? We're going to assume that it does say random right there. Our population is all M&Ms. Think about all the M&Ms in the world. Is that greater than 10 times your sample size of 100? Are there more M&Ms in the world than 1,000? Check. N times P, N is 100, P is 0.20, that gives you 20. Is that greater than 10? Check. And everything has to pass. 100 times 1 minus 0.20 is 80. Check. So all three conditions are met. We can find our standard error, square root 0.20, parenthesis 1 minus 0.20, divided by 100, double triple check typing that in. You should get 0.04, don't forget that 0 before the 4. Then we can move on to find our z-score. So to find our z-score, it's p hat 0.15 minus 0.20, which is p, over our standard error, which is 0.04, gives us our negative 1.25 z-score. In our picture, negative 1.25 is here, and we're looking for less than, so I shade less than. Go to the table, look up negative 1.25 for using the table method. You get 0.1056, which is 10.56%. And again, that should make sense. All M&Ms, 20% are orange. The chance of getting less than 15 is going to be small at 10.56%. So there is a 10.56% chance of randomly selecting 100 M&Ms in which 15% or less are orange. Okay? We have more examples that I want you to practice, but we're going to stop this video and give you a chance to practice.